Questions, you can rescue your compatriots. Do you have a question?
I have a question for him.
Uh-oh. No, that's not fair. Okay. So I have a question for you. Which diagram on your shirt is the one we're going to use today? Sorry? Yeah, which diagram? No. We're only going to use this one. Okay, we'll use some other ones later. I think this one will be on the last problem set. Okay. Once again, any questions before we begin? Okay. Well, you can tell your compatriots that today was the wrong day to get up late, because the first thing I'm going to do today is to write down the theory of the strong interactions. And if you come 5 minutes late, you're going to miss it. Actually, we now know more or less everything that we have to know to build the theory of the strong interactions. The ingredients of the theory of the strong interactions are, first of all, that the matter is quarks, and I'm going to ignore the masses. I can put masses in for the quarks, but we'll do that later. The second thing is that I need some kind of extra particle that's going to bind the quarks together. So I need some kind of binding force. And that force has to be asymptotically free. And that means that it has to be a Young-Mills theory. Actually, in the last lecture, I argued that Young-Mills theory is asymptotically free, but I didn't argue that it's the only possibility. However, it is. You can just go through and catalog all the renormalizable quantum field theories and compute the beta functions in all of these theories. Actually, one of the claims to fame of Tony Z, the author of one of your quantum field theory books, is that in 1972 he did this exercise. He computed the beta function in every renormalizable quantum field theory except for Young-Mills theory, for which the technology was still under development, and always found positive beta functions and was very frustrated. And so it has to be a Young-Mills theory if it's a renormalizable. Oh, and let me put renormalizable. Yes?
People that did calculate the Young-Mills beta functions got Nobel Prizes.
Yes.
So that's kind of a...
Yes. No, you're wrong. The 4 people who calculated the Young-Mills beta function got Nobel Prizes, because you have to include Mr. Toft, who did it a year before the other guys. But there's a whole story about that, which I won't explain. And then finally, we need to have the mesons and baryons as at least the most stable bound states of quarks. And so we have to be able to explain that as well. One property of strongly coupled Young-Mills theory is that so this is a Young-Mills theory of some gauge group G. The bound states are G singlets. So why exactly this is, I'm not going to explain to you clearly, but I think it's reasonable, at least that the low-lying states should be singlets under the group that corresponds to binding things together. And so what kind of theory is it then which is asymptotically free and leads to G singlets? So the first question is, what is the quantum number of G that these, whatever the Yang-Mills bosons, couple to? And I think you can see from my description of quarks that there's only one quantum number available that isn't already used. We've used the flavor. We can't couple to the spin. That would create some kind of higher spin theory. The only quantum number available is color. So we need a theory that has, and color comes in threes, so we need a three-dimensional representation. So then there are only two possibilities available, SO3 or SU3. In SU3, very conveniently, there are two kinds of invariants, delta ij and epsilon ijk. This one would put together a 3 and a 3 bar to make a singlet. This one would put together 3 3s to make a singlet. Those are the mesons invariants. Over here, there are the same two possibilities, except that there's no 3 bar. So this one also puts together a 3 and a 3, which would mean that there would be di-quark bound states which are not observed in nature. So such a thing would be an SO3, but not an SU3 singlet. Yes?
What does it mean?
I'm sorry?
What does it mean?
Oh, it means that if I is the color, that quantity is an SU3 invariant. Okay? Which it obviously is. So here we get the mesons and the baryons. Here we get some other thing. So this must be wrong. So now we're down to one theory. So,
I'm sorry, I don't know what you mean.
sorry?
I don't know what you mean by A sub 3 in the delta ij gives 3 plus 3.
Oh, well, in SO3, there's no distinction between a 3 and a 3 bar. All the representations are real. It's just a three-dimensional vector. So then if I have a quark that has 3 colors, and I put it together with another quark that has 3 colors, and sum over I, this is a singlet of SO3. If I assign this to be an SO3, a vector quantum number. So then there would be di-quark states that we would see in nature. But we don't see any di-quark states in nature. We only see baryons that have 3 quarks. So this must not be the right answer. Yes?
I'm sorry, what do you mean by 3 and 3 bar?
Oh. So if I have the action of SU3 is a unitary 3 by 3 matrix. And by 3 bar, what I mean is the opposite action. AB, alpha, beta, gamma goes to alpha, beta, gamma, U dagger. Now, in SU2, these are actually equivalent representations. One is they're connected by an overall unitary transformation. In SU3, these are distinct irreducible representations. So there are 2 distinct representations which are complex conjugates of each other, but which are not equivalent. The quarks, the 3 colors of quark correspond to one. The 3 anticolors of antiquark correspond to the other. In SO3, those 2 representations become equivalent. SO3 is a subgroup of SU3. within SO3, those two representations are equivalent, and they just correspond to the representation of a vector in three-dimensional space. So in SO3, I could have a QQ bar bound state, but I could also have a QQ bound state. If I insist on things being a singlet of SU3, the QQ bound state is no longer a singlet, but the QQ bar bound state is. Okay. Okay. So now we're done. So now let me just write down the theory of the strong interactions. I choose the gauge group SU3. The Lagrangian is -1/4 f mu nu A squared plus the sum over flavors of Q bar I d slash, I can put the masses back if you like, MFQ summed over F equals UDSCBT. And A is summed over the generators of the group SU3, which run from 1 to 8. And that's it. That's the only thing we can write down. And this theory is called QCD, or quantum chromodynamics. Okay. Well, I guess you could say that's pretty interesting. Oh, and one more thing. The bosons here, which come in 8 and their spin 1 vectors, are called gluons. Don't ask me to defend that name, but that's what they're called. Now, it turns out that it's possible to analyze the strong coupling behavior of Yang-Mills theory, not in continuum space-time, but if you replace space-time by a discrete lattice, you can actually take the G goes to coupling constant to infinity limit of Yang-Mills theory and study that limit. And it's a property of that limit that the only states of finite energy are G singlet, color singlet states. So this theory actually does explain why quarks are confined. This is something I'm not going to have time to discuss in the course. I don't know whether Kadanoff mentioned it in his lectures. No. But it's really in the territory that Kadanoff talked about in statistical mechanics. It's possible, by the way, to do computer simulations where you set up a lattice of points, let's say 64 by 64 by 64 by 64. You do numerical computations of correlation functions in the lattice version of quantum chromodynamics. You look for the poles in the Fourier transforms of correlation functions, and you identify those poles with the hadrons of the hadron spectrum. And actually, the current state of those calculations is that you actually get good agreement with the low-lying states of the hadron spectrum to a few percent accuracy. And so there's numerical evidence that this theory really describes the low-lying parts of the strong interaction accurately. However, what I'm going to concentrate on in this lecture are tests of this theory in the high-energy end, where we make use of asymptotic freedom, and the theory is weakly coupled, and then we can do some Feynman diagram calculations and compare them to experiments. Okay. So now let's get a little more quantitative about the high-energy properties of QCD. Once again, the main thing that we've learned from yesterday's lecture is that this is an asymptotically free theory, at least if there are sufficiently few flavors of quarks. So if I write down the expression for the asymptotically free coupling constant, it looks like this. Alpha S at some reference scale. So this would be the solution of the renormalization group equation that I wrote down last time. 1 plus b0 over 2 pi, the log of q over q0, where with the negative sign of the beta function, this coefficient b0 is a positive number, and it's equal to 11/3 times the number of colors minus 2/3 times the number of flavors of quark. And for the model that I've written up here, actually, I'm going to ignore the top quark until the very last week of the course, because the top quark is so heavy it doesn't come in loops in any practical situation. So this thing, you remember, comes from a loop of fermions. And so the momentum flowing through the loop has to be much greater than the mass of the fermion. So in the situations that we'll talk about, U, D, S, C, and B flow in the loop. And then this number is 11 minus 2/3. This number is 3 minus 2/3 times 5, or about 23/3. So 23/3 is a nice, hefty, positive number. And so there's significant running of this coupling, at least on a log scale, over a regime that we can access and experiment. And just to give some idea, when we analyze the experiments, this number turns out to be about 0.18 at about 10 GeV, and something like 0.12 at 100 GeV. Actually, the modern determinations are really, really accurate. And the only problem with this is people quarrel about the 5. Many people think it's an 8. But we'll leave that aside. Let me put these numbers back just to give you an idea. This is the strength of the coupling. And over the regime that's been observed experimentally, it has significant variation. And how you get those numbers is the next thing that I'd like to explain. Okay. Well, the first thing you notice about these numbers are that they aren't zero. And we have introduced new particles in the theory, namely the gluons. And so those things ought to somehow show up experimentally. It can't really be true, as I was trying to persuade you last week, that we can totally ignore the strong interactions. It's just that for high momentum transfer, the strong interactions are a subdominant effect. And so now that we have a theory, we can go back and compute, well, exactly how big is that effect, and how do you look for it? So a reasonable place to start is by going back to E plus E minus annihilation and drawing the diagrams that would occur if we had this complete theory, quantum chromodynamics. And I'm going to think about large momentum transfers everywhere, so I'm going to do perturbation theory. So the leading diagram is just the one that we computed in last Wednesday and Thursday's lecture, where I have E plus E minus going to quarks with no gluons around. But then at the next order in perturbation theory, there are some more diagrams where I emit a gluon, and then there's some self-energy diagrams like that. Okay. So all of these diagrams would appear at the next order in perturbation theory. What I would have to do is these processes are all indistinguishable from this one in terms of the initial and final states. So I'd have to sum these 4 diagrams and square the result. And that would give a I'm going to call the coupling constant, I used the notation over here, alpha S. So that plus that plus that times that gives an effect of order alpha S. And then these 2 diagrams, if you sum them and square them, gives an effect of order alpha S. And that would provide an alpha S correction, which would affect the total rate. And it also affects what the final states look like. Yes? g squared. So the correction to, yes?
Second and the third, they have propagated that goes nowhere.
No, they have a gluon emitted into the final state. They actually emit a gluon. Free gluon, yes.
Then it's a different process.
Yeah. So what I want to do, I'm sorry, is I want to take this and square it plus is that okay? That's what this lecture is about. Okay. So, so now if you actually do this calculation, what you come up with is the following result, that the cross-section for E plus E minus to strongly interacting things is equal to the cross-section for muons. So in the last lecture, I claimed this result times the factor QF squared times 3. And then if you actually compute all these diagrams, you get an extra alpha S of the momentum transfer of S over pi. And there are higher order terms. Actually, the next few terms in the series are now known. At 100 GeV, this is about a 4% correction. At 10 GeV, it's a 6% correction. And actually, this factor accounts for that difference that you might have noticed in the curves before between the naive value of this ratio of these two cross-sections and the actual experimental data. So this little shift actually is mainly accounted for by this term, which corresponds to the effects of gluon emission. Now that in itself is not very strong evidence. What you would really like to do is to visualize these diagrams where gluons are actually emitted and think about what they look like in nature. So let's now discuss that topic. Okay, so now what I would like to do is to compute these diagrams. It's not so hard. It's, there's nothing really non-abelian about it. It's basically a quantum electrodynamics calculation dressed up. First of all, we should do the kinematics. So I think let's call this Q. Let's call its momentum K1. Here's Q bar. Let's call its momentum K2. Here's the gluon. Let's call its momentum K3. Now, the momentum that goes in here I'm going to call Q. And now we need to express this in some appropriate coordinates. But how many of you did the homework, by the way? Ah, very good. Okay. So if you did the homework, you know all about three-body phase space. And so that's a very convenient way to express what's going on here. Let me define variables x1 is equal to 2 k1 dot q over q squared. x2 is 2 k2 dot q over q squared. x3 is 2 k3 dot q over q squared. x1 plus x2 plus x3 is equal to 2. k1 plus k2 plus k3 is equal to q. And these are very convenient variables to express what's going on in this process. And so in terms of these variables, you can then just reduce and compute the Feynman diagrams. It's a nice exercise that those of you who are interested in particle physics should do. But I'm not going to do it out. I'm just going to write down the answer. D sigma dx1 d. Oh, and the phase space region in terms of x1 and x2, each of these quantities has a maximum value of 1, which corresponds to a configuration where, let's say, the quark is moving this way, and the anti-quark and the gluon are recoiling directly against it. So in that case, the quark has a maximum energy which is a half the energy of Q in its center of mass frame. And that corresponds to a value of 1 for this expression. So if everything's massless, there are kinematic boundaries at 1. This diagram over here would correspond to x1 equals 1, x2 equals 1, and x3 equals 0, which is to say this point. And what these diagrams do is that they populate a region of this plane, which is this triangle here, that you folks will recognize if you did the homework. Okay? Good. And if the gluon is soft, then mainly you'll be up in this corner. And if the gluon is harder, then you come down in this direction. Yes? High energy or low energy. So if the gluon has zero energy, you're still up in this corner. And the points along this line correspond to the gluon at its maximum energy and the quark and antiquark recoiling against it. Okay. Okay, so let me now write down this cross-section. The one thing that you might need when you calculate the cross-section is that in Yang-Mills theory, the vertex has an I, a G sub S, and then a group matrix. And when you calculate this, you need to know that the trace of TATB is canonically normalized to a half delta AB. And that the number of colors is 3. So I won't go through any more details. Let me just write down the answer. dx1 dx2 is equal to 2 alpha s over 3 pi times sigma 0, which is this cross-section, times the behavior x1 squared plus x2 squared over 1 minus x1, 1 minus x2. So oddly, this cross-section, if you compute it from those diagrams, is singular along this axis and along this axis, with maybe I should say a double singularity in this corner here. But nevertheless, if you have x1, x2, and x3 in the center of the diagram, there's a non-zero result. So if somehow we were to exclude these regions, we could talk about the density of population of this phase space and use this formula. Okay. Well, all kinds of questions arise here. Later in the lecture, I'll give you a partial derivation of this formula. That is, we'll derive it in some asymptotic limits. It's not hard to derive the whole formula. It just takes more work than I have time for. Okay. So this number here is something like 3%. This number here is singular. So probably you would estimate from this that about 10% of E plus E minus annihilation events should have a visible gluon, whatever that is. Now, I hope you all brought your laptop so you can look at the PDF figures for today's lecture. If you look at figure 2, what you see is one of these quark-antiquark annihilation events of the form. Oh, just look on with somebody else. There aren't so many pictures. Okay. Nope. It's not in there. Okay. If you look at figure 2, what you see is one of these quark-antiquark annihilation events with a jet recoiling against another jet. However, if you take more data, you see pictures of a different kind. Page 3 has a picture with 3 jets. So somehow what's radiated in that case are 3 different clusters of particles, probably, I would like you to believe, corresponding to 3 primordial objects. On page 4, I think I even have an event picture with 4 jets. So then you have the Q and the Q bar and 2 more primordial things radiated off it. And so if we interpret those, each jet is a quark or a gluon, we can ask the question, do these jets have the correct distribution in phase space in order to account for the radiation that's predicted by quantum chromodynamics? Maybe I should also say that these diagrams have exactly the structure of electrodynamics. So basically, the question we're asking here is, is the pattern of gluon radiation the same as the pattern of photon radiation from outgoing quarks and gluons? So there are various ways to answer that question. One way is just to try and approach this formula in such a way that we can, of course, this formula has divergences all over the place, but we can try to approach this formula in such a way that we can make some quantitative prediction from it and compare that prediction to experiment. So here's a way to do it. We can ask, if I have an event of this kind with tracks all over the place, to what extent are these tracks all lined up along a given axis? And to what extent are they spread out perpendicular to that axis? So you can invent a variable that quantifies that. And a very convenient one is called the thrust. Now, so the thrust is defined in the following way. You take the sum over all the tracks that you observe in the event. You add up the magnitude of the momentum of each particle. You take an axis and you look at the momentum along that axis, and then you choose the axis in such a way as to maximize this expression. So n is a unit vector. And I'm going to choose that unit vector probably like this for this event in such a way that the tracks are maximally lined up along that axis. And then I ask, what fraction of the total momenta of tracks is projected along that axis? And the picture here is that if QCD basically accounts for the momentum flow, so I have an event like this with a Q bar, and a gluon, that I'll make these objects. These will then turn into a shower of particles. But if QCD accounts for the momentum flow, it should predict the distribution of this quantity. By the way, thrust is an object lesson to all of you who wish to discover new things in physics. It was invented by a friend of mine named Eddie Fari, who called it spherosity. Which was not a very good idea, because then his competitors at CERN said, oh, we'll invent a variable which is actually the same variable, but we'll call it thrust. And that's the name that stuck. OK. So now, can I compute the thrust from this formula? Well, it's actually not very hard. If you look at this diagram, you can see that I can subject the same analysis that I did on the tracks, I can do on the ingredients, the partons, the ingredients in this calculation. In fact, there are only 3 obvious choices of the best axis. You'll want to line it up with one of the partons and sacrifice the other 2. And so in a configuration like this, thrust is equal to the maximum value of x1, x2, and x3. And so then what you can do is just compute d sigma dt by integrating over the direction in this plane orthogonal to the thrust. So if I divide this region into 3 parts, in this region, the thrust is equal to x1, so I can integrate over lines of constant x1. In this region, the thrust is equal to x2, so I can integrate over lines of constant x2. And in this region, the thrust is equal to x3, so I can integrate over lines of constant x3. And if I do that, I get a definite expression, which I think I'm even going to write down for you. d sigma dt is equal to times 1 over sigma 0 is this 2 alpha s over 3 pi coefficient. And then there's a definite expression, 3t squared minus 3t plus 2 over t times 1 minus t times the logarithm of 2t minus 1 over 1 minus t minus 3 tt minus 3t minus 2 times 2 minus t divided by 1 minus t. Okay, what are the properties of this expression? Well, first of all, when t is equal to 1, that corresponds to a configuration when the quark is back-to-back with the anti-quark and the gluon, or something like that. Remember that in these situations, there's a singularity. It corresponds to x going to 1 or y going to 1. So this quantity has to diverge when 1 minus t goes to 0, and indeed it does. The second thing is that the minimum value of the thrust occurs at this point where t is equal to 2/3. So in a 3-particle configuration, this quantity must vanish when t equals 2/3. And indeed, you see that in several of these expressions. And in general, what you'll get from this formula is some distribution that looks like this as a function of 1 minus t. So on the next page, I think it's page 5 of the PDF, what you see is data taken by this SLD detector, which gives the values of thrust, the value of d sigma d thrust for e plus e minus annihilation to quarks at the z0. And maybe I should just say that the curve that it's fitted to rounds off here, which is not a property of this calculation, but it's a property of something that I'll tell you about in a little while. The curve also extends out beyond 1/3 because you can get lower values of thrust if you have 4 particles in the final state, all the way down to 1/2, I think. But nevertheless, what you see is that the thrust distribution has this qualitative form, and quantitatively it's in good agreement with the predictions of QCD if you compute to higher order in perturbation theory. And by fitting the normalization of that curve, you can get a value of alpha s, which is how I obtained those values that I showed you a little while ago. Sorry? I will explain that. But very roughly, the curve that you see looks like this. And the piece of it from here to here is roughly in agreement with this one. What happens out here is that you take into account more particles in the final state, which allows you to go beyond 1/3. And what happens over here, I have to explain. And I'll spend the rest of the lecture doing that. OK. Good. So maybe I should show you one more plot before we do some more, or a couple more plots before we do some more theory. If you turn to the next page, what you see are a number of determinations of alpha s from, I think, all the ones, I'm not sure what color it is. They're, the ones called e plus e minus annihilation are all of this type with experiments at different energies. And so if you look at the red points on that curve. I don't have color here, but you have color. If you look at the red points, you'll see that as a function of energy, they cover the whole range of the plot, and they correspond to a large change in alpha s from a high value on the left to a lower value on the right. And this is exactly an experimental measurement of the running of alpha s. So these points measure the beta function, and the value that they measure is in good agreement with QCD. The QCD prediction is the fit line that you see on that curve. So yeah, you can measure alpha s at different values of q. It really does change. It really does observably get smaller in the sense that this distribution goes down in normalization at high energy. And so asymptotic freedom is not only a theoretical property of Yang-Mills theory, it's actually something you observe in the data. Okay. Now, there's a lot more that I want to tell you about this formula. And so to do the next thing, what I'd like to do is to derive that formula in the collinear limit, where the gluon emission is almost collinear to the quark or the antiquark. So let me try and set up that calculation and tell you some things about it. So let me think about a situation, the following situation. I create a quark and an antiquark, and then I let that quark radiate a gluon which is almost collinear with the quark itself. So let me call these momenta k and q. And I think in my notes I call this off-shell momentum here p. And what I'd like to do is to compute the gluon radiation rate in the limit where these two guys are almost parallel to one another. Now this is a relevant limit for the following reason. If I think about the propagator on this line, it's 1 over p squared, which is 1 over k plus q squared. And I'm treating all these particles as massless. I'm in the high energy limit. This is 2k dot q, which is equal to 2kq times 1 minus cosine theta, which is the angle between them. Well, now you see something very interesting. If cosine theta equals 1, which is to say the quark and the gluon are parallel, this quantity is 0. And it doesn't require a soft gluon in order to get 0. For massless particles, you actually get 0 for any momentum splitting between k and q, just provided the particles are collinear. So this is called a collinear singularity, or sometimes called a mass singularity, because it appears in the limit of 0 mass. It's a singularity which is quite distinct from the soft singularities that you folks might have encountered in your quantum field theory course. In fact, this diagram will have both soft and collinear singularities, as we'll see. This collinear singularity has a very important effect on the development of radiation in QCD, actually also in QED, although in QCD the coupling constant's larger and it's a more dramatic effect. What it means is that if I have a quark going along, there's a very high probability that that quark will share its momentum with a gluon, and then actually these particles begin to split and share their momenta with other particles in such a way that as we continue the process, we can develop very complicated final states of quarks and gluons. Then eventually those final states can reform, as they have to because of quark confinement, into hadrons. But as long as we're in the perturbative region of this process, we can use Feynman diagrams to compute what's going on. And so I'd like to try and use that as a method of analysis. So let's now compute the rate for this particular kind of collinear splitting. To do that, let's put some coordinates on this. So let me write Q. Let me, first of all, write P is equal to E, 0, 0, E. Actually, this isn't going to be exactly right, but I'll fix it up in a moment. Q is equal to ZE, and K is equal to 1 minus Z times E, where Z is some number between 0 and 1. So Z is the momentum fraction of the originally created quark, which is carried off by the gluon. There's some angle here, otherwise it would really be infinity. So let me put KT as the transverse momentum of the gluon relative to the original quark. That has to be balanced by this transverse momentum. Let me, just for convenience, put that in the the 1 plane. And then what we need here is the momentum in the forward direction. And now this particle has to remain on mass shell. So that's going to be something like ZE minus KT squared over 2ZE, plus order k to the 4th. So if you square this, and you add the square of that, you come to the square of this, and the particle is massless. Similarly, down here, we have to write 1 minus ZE minus KT squared over 2, 1 minus ZE, plus order k to the 4th. From now on, let me just assume that KT is much smaller than E, and I'm always just keeping the lowest approximation that I can in that limit. Sorry? Yes. Okay. And now I have one more thing to fix up. I need to fix this guy, because the one thing I know about is there's momentum conservation. So this momentum, which is off, here I've written it as on shell, but actually it's off shell. And it had better add up to the sum of these two momenta. And so this should be E minus KT squared over 2E. And then 1 over Z and 1 over 1 minus Z is 1 over Z times 1 minus Z. Okay. So I obtained this by insisting that this vector should be the sum of these two, as is indicated by the Feynman diagram. Okay. Actually, now we can find out exactly how off-shell this particle is. If I just compute p squared, I get kt squared. This cancels the leading square of that. What's left over, sorry, we're up here. This squared cancels that squared. Yeah, that's right. What's left over is the cross term. It's E0 squared minus p squared, so it comes in with a plus sign. And the answer is kt over z times 1 minus z. So this line is, please notice, has a very strong singularity in different limits. First of all, it's singular when z goes to 0. That's a soft limit. It's singular when 1 minus z goes to 0. That's the other soft limit. And it's singular when kt, sorry, I just said a wrong thing. Let me take that back. It's singular when kt squared goes to 0, which is to say that's the collinear limit. Just forget the other thing I said. I was getting ahead of myself. Okay. Well, now we have lots of kinematics. Now we're ready to compute the Feynman diagram. Yes? Yeah, so p squared goes to 0 when kt goes to 0. And p squared is in the denominator. Okay. Good. Okay. So now what I'd like to do is to do the following. I'd like to treat this propagator, which is p slash over p squared. I'd like to write that as u of p, u bar of p over p squared. So this u bar I'm going to associate with this process here. So that's basically, if the particle's very close to mass shell, what comes here is just going to be the amplitude for producing E plus E minus to QQ bar that we've already studied in detail. I'm going to take this U and I'm going to associate it with this emission process. And so then I can compute the emission process in the following way. The matrix element for the emission is I G sub S T A, because this is a QCD interaction, U bar of K, gamma mu, epsilon mu star of Q, U of P. So that object describes this vertex. And now what I'd like to do is just compute this, the rate associated with this. Actually, I can use two component fermions. So I can use sigma bar here. And, well, I've already tried to teach you that the right way to think about these things is to use helicity amplitudes. So let's just compute the helicity amplitudes. Actually, there are only two cases. Because helicity is conserved for massless particles, if I start with a left-handed fermion here, this guy is always left-handed, and this guy can be left-handed or right-handed. And so there are those two cases. The case where this guy starts out right-handed are just the parity conjugates. And because this theory I wrote down is actually parity invariant, I'll get the same expressions. Okay, so now we just have to put in the right things. U of p, the two-component fermion, is the square root of 1 minus z 2 times the energy, which is 1 minus z times E, times 0, 1. Sorry. That isn't what I wanted to write. U of p is the square root of 2e times 0, 1. U of k is the following thing. First of all, it's got a 1 minus z times E because its energy is 1 minus z. Secondly, it's slightly rotated. The particle is slightly rotated from the 3-axis. And so instead of being 1, 0, it'll have kt over 2 times 1 minus z times E up here. And then I need to write down the polarization vectors. So there are left and right-handed polarization vectors for the gluon. For the left-handed vector, that vector is 1 over the square root of 2, 0, 1, I. And then, once again, it's rotated by an angle kt over ze. So these are the appropriate polarization vectors. Let me just see. I think there's a minus sign here. So this vector has to be such that when you dot it with this momentum, it gives 0. And you can see that that times that, if it's positive, requires that times that to be negative. Okay. So these guys, again, satisfy epsilon dot q is equal to 0 to a first order in kt. And that's all we'll need. Okay. Now we're doing excellently. Now let's calculate sigma dot epsilon star, which is what appears in this expression. In this case, it's 1 over the square root of 2. The one term, 1 and I and minus I, because it's epsilon star, will give a 2 up here and a 0 down here. In this case, we'll get a 2 down here and a 0 up here. And then these extra terms will give kt over ze here and kt over ze here. And you just have to be a little careful where the minus sign is. It's here. Okay. Okay, very good. So now I just take this matrix, I evaluate it between these spinors, and I can calculate the matrix elements. So let's start off with this case over here. Please notice that the 2 is in exactly the place where it's going to annihilate 2 multiplied into that is going to give 0. So the only term we get is the diagonal term between this, this, and this. And so in this case, we'll get just kt over 2e times various other factors that appear, I, g, ta, 2, the square root of 1 minus z, and e from these prefactors. And I think that's the whole, oh, sorry, kt over z e is what we should have gotten. And so this is now the whole expression. A factor of g, a group matrix, 1 power of kt, the e's cancel, the square root of 1 minus z, and a 1 over z. And very good. Now over here, we get that same contribution, but there's another contribution that comes from that times that times that, which is kt over 1 minus z. And so the answer here turns out to be the same answer that we got over there with times kt with an extra factor of 1 over z, 1 minus z. Okay. Well, excellent. So now we're just doing extremely well. Oh, I'm sorry. I left out one more thing, which is this 1 over the square root of 2 in front of this. So this should be the square root of 2. Good. Okay. So now we can go back over here and try and reconstruct this whole part of the Feynman diagram. Is equal to 2g squared. If I square this TA, and let's see, and I want to sum over a final color and spin, TA is 4/3 in SU2. So that gives this factor. There's a 1 minus z, there's a kt squared, and there's a z squared and a 1 minus, sorry, there's a kt squared over z squared. That's present in both cases. And then there's a 1 plus 1 over 1 minus z squared. So in the end, what we get is this, times 4/3 times kt squared times 1 minus z over z squared times 1 plus 1 minus z squared over 1 minus z squared. Okay. Very good. Okay. Yes.
The polarization vectors, if that form that they are slightly rotated
Yes.
with respect to Z, is that why they have a Z component?
Yeah. What I need is this. This is what I need fundamentally. Right. And so because the gluon was slightly rotated, the polarization vectors also have to be slightly rotated to satisfy that condition. And if you check, maybe I did it too quickly, we can get the signs right by imposing that condition. Good. Okay. Well, now we're almost done. Now all I have to do is to think about the phase space of the gluon emission and rearrange the phase space in a way that's compatible with this expression. And so what I'd like to do is to write that in the following way. The phase space is d3k over 2 pi cubed 1 over 2k, d3q over 2 pi cubed 1 over 2q. There's a momentum conserving delta function, and there's one more part of this which is very important, which is there's this propagator, which is 1 over p squared squared. And so let me try and rearrange this in such a way that it's in a useful form. So first of all, let me take out of let me keep what I'd like to have is the integral d3p over 2 pi cubed 1 over 2p. And that's related to this integral here. That's related to that integral. I'm sorry. That's related to that integral in the following way. P is approximately collinear with K with a factor of 1 minus Z. So there'll be a 1 minus Z squared, I think it is. Then in this integral, I can write this as d2kt dq3 divided by q 2q. So this thing here is dz over z. So there'll be a dz over z. There'll be a d2k. This thing will remain around, so there's a 16 pi cubed. And then the last piece of this is 1 over p squared, which I wrote up here, which is kt to the 4th divided by z squared times 1 minus z squared. Okay. Well, now things are working out kind of nicely. We've got the integral over the final quark, over the quark here, which I'm going to push into the cross-section calculation for this process. So I'm going to write the cross-section for e plus e minus to q bar gluon is equal to the cross-section for e plus e minus to q bar. So I need to keep all the factors associated with that, and that includes this factor here. Then I have an integral d2 kt. Let me write that as an integral pi dkt squared divided by kt to the 4th. And when I square up these matrix elements, I'm going to get a kt squared. So this is kt squared here. There's left over here a 16 pi cubed. There's a g squared in both of these expressions. there's this 4/3. There's that factor of 2 out there. And then there are various factors of z. So this expression here has a z times 1 minus z. If I square that, or you see here there's a z squared and 1 minus z squared, that exactly cancels what's in the numerator here. And so what's left over is this 1 minus z, and that factor over there of 1 plus 1 minus z squared. Very good. So now we're really almost there. This thing will combine into an alpha s. And so I claim that we now get the following answer. 4/3 alpha s over 2 pi, the integral dkt squared over kt squared. Oh, I'm sorry, I left out an integral dz over z. There was one more factor of z that I needed to cancel that. Oh, no. Yes. Oh, what I wrote was d3k over 2 pi cubed 1 over 2k. So that's the phase space integral over this quark. Because these guys are collinear, I can write this as the integral d3p over 2 pi cubed 1 over 2p. And then there's a scaling here. There's a 1 over 1 minus z squared. Okay. So, in fact, that's exactly the mistake I made. This is a z and a 1 minus z squared. So, please excuse me. What is supposed to happen is that all the 1 over z squareds cancel, and a 1 over z is left over. And I'm really not seeing right now how that works, but it's actually correct. If you go to the notes, you'll see that it works. So there's an integral dz, and then what appears here is 4/3 alpha s over pi, 1 plus 1 minus z squared over z. So please excuse me that I haven't made the cleanest work of this derivation. It's actually correct in the notes. And the final answer is this. So, sorry? The hour's almost over, so let me just say this for now. I'm sorry, it's too early in the morning, but it's correct in the notes. The physics of this is the following. This thing is a logarithmic integral, and that logarithmic integral reflects the collinear singularity. If I take kt to 0, or take kt to some cutoff, the log of that cutoff appears. So this is a factor of the log of the original momentum divided by the let me write mu, the smallest value of kt. So there's a logarithmically enhanced probability that I'll radiate more and more collinear gluons. This 1 over z here is the soft singularity. So there's also a logarithmically enhanced probability that I'll radiate soft gluons. And then the normalization is determined by alpha S. And by the way, this 1 comes from a left-handed quark radiating a parallel gluon, parallel helicity gluon. And the 1 minus Z comes from a left-handed quark radiating an anti-parallel helicity gluon. So all the aspects of this formula, if I could ever derive it correctly, have a very good physical interpretation. So I think it's late. I'm going to stop here. We'll pick the subject up tomorrow, and I'll tell you about the phenomenological applications of this formula. Okay. Yes? Oh, yeah. I'm sorry. I think well, okay. The lecture's over. If anyone's interested where I made all the mistakes, you can hang around for 5 minutes. And I'm gonna